Right. Hello, everyone. Another week. Okay. So last lecture we have Paul here give us a guest lecture just to open up the whole so to open up the whole educational program. So today we're going to start the first lecture, it's a technical lecture. So I will be cover some physics part about MRI. Yes. Okay. So first part will be I just use 5 minutes to cover about some physics on
you want to wait for a moment? If you're in the Zoom, can you hear Guorong well? Just to confirm.
Yes, we can hear you.
All right, thank you.
So, okay, so this is the camera. Yeah. Right. So first we'll talk about the physics about the MR. How does the MR works? And then I'm going to dive into the two parts. First is just very fundamental, just to clear up some concept about image processing. So we're going to talk about what is what's a header file, what is image intensity, and how do we do tissue segmentation, registration, and what is atlas. We often heard this buzzword in the following lectures. So what is atlas? And after that, we're going to showcase the image processing pipeline just from the beginning, right after you do the scan, from the PACS, the system and to the server, and then we start to process the 3D image and all the way down to the the brain surface, the structures. So basically today we're going to talk about the human brain, right? So this is the human brain, okay? So we're going to study this, okay? So before we do that, let me ask you a question. Anyone can tell me which one is the left and which one is the right? Which part is the left brain or which part is the right hemisphere? Right. This is left, like this. This is left.
That's right.
That is right. So basically, this is our eyes. Right? This is eyes right here. Right. So basically, this is basically nose is here. Okay. Eyes is here. Okay. Visual cortex right here. Okay. You process all the visual stuff here and this is process a lot of things like cognition, behavior. Your behavior, emotion, everything by. This is called the frontal lobe. Okay, so today we're going to study this. Okay, so human is a right, we already had this slide. Okay, so human is a very complex. I would say the most complex organ in our body. Okay, so how to study our brain? So this is our brain. This is the skull. Okay, this is our skull. The heart. It's very hard. Okay, and this is the brainstem. Okay, so before the technology. This MR technology coming out, we have no way to study the brain. Okay, only thing we can do is we can just we talk and then we try to guess what what's going on in the brain. Okay, now we have this MR machine. So the MR machine is nothing but a organic the magnetic. Okay, so this is our magnetic. Okay, so usually when you're going to take an MR scan, you just you just lay down that table. Okay, they will put on a coil here. I'm not sure it's okay. This is a coil. Okay, something like a helmet. Okay, put in your on your head. Okay, and they will give you some the earbuds. Okay, because this machine is very very loud. Okay, and then you get on this, and then they push the button. The people help you on this. Put the coil on, they will leave this room. Okay, they will go to a computer room, and they push the button, and then you're going to add into this machine. Okay, so what this machine is doing is measure the water. Okay, so why we say that? Because most part of our body is water molecules. Okay, so water molecule, there's if we write down there, the chemical compound is there's a two. Hydrogen, proton, and one oxygen. Okay, and this is kind of like an electron. So basically, it's kind of like without if this is two, the hydrogen proton is basically like rotate. If this is head to the north, this is the tail to the south. Some are going like this, and some are going this, okay? And some are going all the way around, okay? So basically the random, kind of like a random, okay? But if your brain is into this magnetic, okay, we have the south pole and the north pole, okay? So basically all the molecules, they are aligned, okay? Half of them will moving up like south north, another half will be heading down, okay, north to south, like this, okay, right? Literally the half to half, okay. So in the literature, if there's one for every 10,000 of this, the proton, like will be like a 4, 9, 9, 9, 7 will heading north pole, and another 50,003 will go different direction. Okay, so only difference is only 6. Okay, but that is already enough for us to capture the signal. Okay, so basically all the signal is based on this physics, principle. Okay, so this is the difference. We capture, the difference. Okay, but as I mentioned earlier, when you get into the scanner, we'll put a coil in there. Okay, a coil. So what is coil? So basically, we put on, plug in the electricity. Okay, so there's the electricity all around your head. So basically, what they're doing is, if you have taken MR scan, how many of you have taken the MR scan before? Nobody? All right. Can you push the button to play the audio? No, play the audio. Okay. So I'm going to show you what's the audio like this when you in the MR scan. Okay. This like buzzword. Okay. Okay. So what is this sound? Okay. So basically, what we are doing is, as I mentioned, if we only have this magnetic, okay, the only half of the the proton is going this way and another is going that way, right? They still have. We don't know, in the brain we see that there's different tissue types. Basically, no difference. Okay, so how to enhance, how to get that contrast? So what we're doing is we use the electron in this coil. Okay, so basically what we're doing is that this all the molecule is doing like this way. We just flip it. Okay, it's a very short, very brief time point. Okay, we just flip when you hear that the buzz sound. Okay, what they're doing is they maybe half of them are doing this, half doing that, and then after we get this through the coil, we're going to flip. Okay, all the water molecule is going that way. Okay, because we have the coil, we give this some external stimulus. Okay, all the molecules are going that way, right? And then we stop, and then we stop. And then those molecules will gradually going to their previous, the status like this. Half are going up and half are going down. Okay, so this is the time we call it relaxation time. Okay, so it depends on the density of the molecule in the brain. Okay, so this is our scalp. So basically, there's a very small amount of the water molecule there, and this white, this black, the fluid is kind of we call the spinal fluid, cerebral spinal fluid. So we oftentimes the short name for this is called CSF. Okay, so basically this is the fluid. So basically they're connected to your spine. Okay, it's very important. Like if you hit the wall, this kind of help protect the brain. Okay. And of course, there's a lot, because this is fluid, so there's a lot of the molecules in there. So that's why we see the contrast. Okay, all the molecules we flip it. Some are take much longer time to going back to the original status. Okay, so that's why we see the contrast. This is a very, very bright. Okay, basically there's no molecule. That's assumed there's only small amount of water molecule, and this black is basically has a lot of molecules also here. This is the ventricle. Okay, it's also connected to the spine. So we see here is a dark. Okay, and some are white matter, some are gray matter. So what is gray matter? Because we call it gray matter. We call it gray matter because the intensity in the MR is in the gray area. Okay, but what is this? This is neuron. Okay. This is neurons. So this is very, very important. Okay, and the the stuff in the middle is bright, close to the white color. So we call it white matter. So what is the white matter? Okay. White matter is basically a lot because brain is only the only user energy. Okay, brain cannot generate energy. All the energy is our human body, digestive system, all the way to the liver, and they provide the the nutrition. And the brain, when the brain working, brain need nutrition, need a supply, need energy. So those energies connect to the fiber or nerve fiber all the way through the through the neck and go inside. Basically, if you open the brain, cut this way, we see a lot of like white matter fibers. Okay, so next lecture we have our Dr. Stanley will come to talk about DWI. So basically, this is a more advanced technology. Basically, we can measure the fibers, okay, how these regions are connected one to another. Okay, so yeah, so this is a very basic about the physics of physics of medical MRI. Okay, so basically is just this is a big magnetic, okay, and all the neurons, all the molecules like halfway like the south north and then halfway is north south. Okay, and we give we use this coil to flick the molecules. Okay, they go in the same direction, and then we just wait to see how long it takes for each tissue type to going back to the normal status. Okay, so that is time is the contrast, in this MRI image. Okay, of course, there's a lot of physics in this, how to design a machine and how to programming the sequence, because you play this one more time, because this is really related to the tissue you are going to looking at. Okay, because see that is a frequency, so that is a common frequency has to be resonance to the tissue. So that's why we call this MRI. R stands for the resonance. Okay, so you have to carefully design this frequency aligned with the tissue. Okay, all right. So it's complicated. So there's another topic, but today we're just going to use a couple minutes to walk you through the very, very basics about MR. How we can use this machine to get the MR image. Okay, and then we're going to start from here to talk about how to process this image, right? So we can move on to the next slides. All right. So there's something like before we work on the image, there's something we need, to have some standard. Okay. So first is because this is the 3D image, right? So we have to have a standard, manner to describe the image. What is X, what is Y, and what is Z? Okay, because it's a 3D image. For the 2D image, we don't have a problem because we see this is the face, it's upside down, or we just rotate. But in MR, like the first question asked, which part is left, which part is right, right? So we have to make sure what is the coordinate system of this 3D. Okay, so what we usually use, we use the right-hand system. Okay, so this is X and Y, and then this is my Z. Okay, so let's go to the next slide. So basically, suppose you are doing the MR. So when you're doing MR, you just facing up. Okay, so if I'm doing this way, this is my left, this is my right, and this is my top. This is the bottom. So top we usually use anterior, and the downward we use the posterior, and the superior and the posterior. Okay, so this is kind of like terms often used in the radiology. Okay, so so left right is a common way of using, but posterior, anterior, and superior and something right. Anyway, so posterior, anterior, and left and right, and what is that? What am I missing? Okay, I forgot one. Anyway, let's go to the next slide. So okay, yeah, okay, here we have, okay. So depends on, because this is a 3D image, right? But when we display the image, we usually only can look at 2D. Okay, it really depends on the view that you are looking at. Okay, so this is a human body. Okay, if we look at this way, okay, so basically we will see left and right. Okay, this is what we call a transverse plane. Okay, this is basically is we are talking about the XY plane. We also can like this, we look at left or right. Okay, basically we cut the view is through here. So basically we can see the inferior and superior. Like the word superior and inferior. Okay, and then we can also look at the brain in the. Okay, so this is called the coronal view, and another view is the section view. Okay, so really depend on the 2D, like a 2D projection from the 3D view. Okay, and so this is a term used in the radiology. When you read a paper, usually when you see this transverse plane, so basically it's kind of like an XY plane. Okay, and this is basically the XZ, and another is the Y. Okay, so let's move on to the next slide. Okay, so but although we have defined the coordinate system, like everything we just follow, but this is my just this, which is the line the left, right, from front to back, and then we use the right hand, right? We can figure out our X, Y, Z, but it's still not still not enough, because let's say this is someone is taking the MR scan, okay, and this is the the physician or radiologist. Basically, they are watching, okay, they are watching the the subject in that way. Okay, so this is my XYZ, okay, and this is the neurosurgeon. So this is doctor, and he's doing the surgery, okay, neurosurgery, and he's looking at the subject, the head in another way. Okay, so when you talk left and the left, basically you have the mirror, right? So how to make it consistent? So we have to make this consistent in the next slide. Oh, no, not next slide. So before we go to the next slide, so we want to talk about the resolution. Okay, so this is another very important concept in medical image. So for the computer vision, for the for the JPEG, or the TIFF, we just know the image size. Okay, it's a 480, 720 by 480. So this is the standard image size. Okay, we don't pay much attention to the spacing of two voxels. Okay, but in the medical image, everyone's brain is similar size. Okay, your brain is big, my brain is similar size. Okay, so we basically put the brain here, right? And the image resolution is nothing. It's not related to image size. Okay, so basically we are reducing the spacing between two voxels. Okay, high resolution, maybe we have more points, sample here, then we can see the picture like much clearer than the low resolution image. Okay, so in medical image, we usually we don't use so-called the unit for image size. In computer vision, we just use a pixel. We just say oftentimes we say, okay, so 20 by 480, right? And so this is the unit for this is a pixel, right? But in medical image, we use the real world coordinate system for the brain. So basically it's 256 millimeter by 256 millimeter by. Okay, but if your image resolution is exactly 1 millimeter, okay, then your image size is 256 by 250 by 256. Okay, but if you're using a better machine, let's say your resolution is 0.5, I don't think we have this high resolution, right? Basically, you double the image size, right? So this is just like a convention in medical field. So we don't use this in the computer vision. Basically, they just count on the points, okay, how many pixels. What we are using is we're basically interested in this, the real, the unit. Are you using millimeter or or micron. Okay, and this is all related to the resolution. Okay, then we can move on to the next slide. Yes, so we talk about how to find a right coordinate system to index the pixels, right? And what is there are a lot of other questions like what is the data type? Okay, is this 8-bit per pixel, or are you using the 16-bit to represent the pixel, right? If you are using the 8-bit, then the intensity range is from 0 to 255. Okay, if you are using 16-bit, then you get a better, like a much wider range to right? So you can get much better contrast for this image. So suppose you're doing image, doing image processing, working on this image will be, you are supposed to get a better result than this one, right? But this one, basically image size is smaller, so for the storage point of view, than this thing, okay? So there's a lot of information we have to specify before we can make this your image like a, then you can really process your image, okay? So then need a standard, okay? So oftentimes we call this is a header file. So all the image, yes, you see it. So all the image, all the images basically is like a cubic, okay? So all the computer can storage this data. So basically it's in a continuous memory space, right? Okay, so basically this is your first pixel or first voxel in your image, right? Then I need to figure out first how many bits, okay? Is this 8 bits or 16 bits, right? And then I'm going to figure out the data is indexed like by the row by row, and then column by column, and then slide by slide, right? So we need this information to read this data, and then we can shape or reshape the two, either to a matrix or a tensor, okay? So all the information is here, okay? So all the image, so current image standard is, when I was a PhD student, we have a file called HDR, okay? So this is the current header, which has 348 bytes, okay? So in binary, so you have to know the structure, and then you can read this 348 bytes, and then basically you're going to get all the information here, okay? And all imaging data is stored in this file, okay? So this is just the binary file, okay? You can read this file if you can read the header right, okay? And now the standard, now the industry standard is we use we call Nifty. So all the image and the header is in a single file. Usually the file extension is NII. Okay. So basically it's the same file, but they use the first 356 bytes to storage this information. Okay. So when you read the image, you need to first read this 356 bytes, and then you're going to get this correct information. Then you're going to read the real image data, okay, and then you can reshape to a matrix or tensor, and then you can go on to the image processor. Okay, so this is about the header file. Yeah, and go on next one. All right, so this is about the image type. Okay, the image, the image file, the data format. If you work on the image, you will see a header file, or sometimes now this one is become popular, Nifty file. Okay, so you work on the real image, we'll give you the example in the Nifty file. Okay, then we're going to talk about image processing. Okay, so why we need image processing? So I want to show you this. Okay, so this is the box. Okay, so this is our brain. Okay, this is brain. Okay, has a very nice shape. Okay, but in MR, what you see in the MR is like this. Okay, this is your image you get. Okay, you don't know what is inside. Okay, because when you see the image, okay, go back to the previous slides. And when the image is like this in this cube, right? So we need to sum our background, right? Sum our background points, sum our brain point, like points in the brain. That is something that I'm interested, right? But some are, a background. Like if you see the background, what you get is like image like this too. Okay, so we need to do segmentation to segment this brain out, okay, from the whole image. Okay, so this is what we call image segmentation, and the different people has different, brain. The size is different, right? Like your hand, someone's hand is big, someone's hand is small, but we will have 5 fingers, right? So we have to align that shape. So this is we call image registration. So go back to next slide. So we need a lot of image processing algorithms, okay, to process the image. So basically what we are doing is we work on image intensity. Okay, so this is the picture that we see. Okay, we see everything, with color. Okay, so what is a computer? What is a computer's? What is the data input that the computer can recognize? Computer only can recognize these numbers. Okay, pixel by pixel. Okay, so we need a set of algorithms to first we're going to recognize which point is which point is background. Okay, and we're going to segment the brain or part of the brain into different regions. Okay, this is the temporal lobe, this is the frontal lobe, temporal lobe, parietal lobe. Everything we give color to each pixel, right? So we need an image object, something like object detection or or region segmentation algorithm. Right? So we're going to work this just briefly. We start from some basic operations that we need to process the image. So first one is a neighborhood operation. So what is neighborhood? Okay, so this is another term we often use in the image processing. So the neighborhood basically is so if for a point, for any point here, then we can define the neighboring points, one point up, left, down, left, right, and down. Okay, so basically this is just this is we oftentimes we call this is the four points neighborhood. Okay, and you can add this and become 9 neighborhoods, and we can make it a larger 3. So this is a 3 by 3, and we can make it 5 by 5. Okay. So why we needed this? Because we sometimes if you want to do the smoothing, right? If there's a pixels here, if there's a noise like stopping point, we want to remove it. So basically, we want to we need to define some operations, work within this neighborhood, and either do average or you do some other like find the maximum number. And once you get that number, you're going to replace number right to this underlying point. Okay, so this is called a neighborhood operation. And another operation we often use is we call it a geometry. Okay, like if you want to rotate the image, okay, basically we want to move this image to a new coordinate. Okay, but there's something that we need to pay attention. So once we get the image, basically this image we call this a digital image. So basically we only have the values on this point, on this grid point. Okay, we have the intended values on this grid point. So basically, let's say x is 20 or y is 30. So basically, this is the integer number, right? But if we do some geometry transformation, we get this x prime and y prime. What if the x prime is, let's say, 25.5, the y prime is 31.25. Okay, so they are not exactly on the grid point, right? There are maybe somewhere here, right? But we don't have the value, we don't have the intensity, we don't have the samples to for this location. So in this case, we need to do interpolation. So we're going to interpolate the values, okay, based on the neighboring point, right? We only have an observation here and here and here and here, okay? So you can do linear interpolation, you can do nearest neighborhood. Basically, we just give, because this one close to this grid point, we just give the value on this grid point to this point, right? And we can do linear interpolation, you can do other, fancy, interpolation methods. So the point here is after geometry transform, you're going to, move this point to a new location, which is not exactly on the grid. Okay, so we need to use interpolation, this operation to, to get the values, and then we can do the geometry transform. All right. So the simple geometry transform is translation. So basically, we just need to estimate the. So this is kind of very general. So basically, this is the 2x2 matrix. So here we just make it simple. This is the 2D case. This is the easy, straightforward extended to 3D. So basically, this is the we need to have these 3 parameters of these 4 parameters which controls the rotation, translation, and the scaling. Right. So we can move on. Okay. So so here is we can extend. So we can let me see again. So this is a matrix A. We often call this is A-prime matrix. A-prime matrix which include all the possible translations like shift. In shift we call the translation and rotation and also the scaling. So basically the size difference. Okay. So we often use the gradient-based or least square method to estimate this parameters. In this 2D case, so basically we have 6 parameters, right? So so basically we just need 6 pair of correspondence from one image to another image. Then we can use the least square fit. We can calculate this this variables, or we can use a gradient-based method to iteratively to optimize this transformation parameters. So you're going to see all kinds of methods, but now it's I think this will all have the closed form solution. All right. So so this slide basically just to show all the possible the geometry distortions. Like the first one is identity. So basically we're doing nothing, okay? And this is the scaling. So scaling is basically the 2 parameters on the diagonal line, basically to control the size. And the translation is easy, just the last column, and also the rotation and sharing. So most of the the transformation in the real world is basically the combination of all of this transformations. Okay, so we already talked about the interpolation. So interpolation is basically like if I rotate the image, right? So basically we probably will end up in this in this location, which is not exactly on the grid point. So we can use the binary interpolation. So basically it's called nearby nearest neighboring interpolation, linear interpolation, or cubic interpolation. So basically so this is kind of like the low pass filtering. This is band pass filtering. We try to get some high order information to make the boundaries looks better, right? If you just do this binary interpolation, you're going to see this jaggedy here, right? It's not good, right? So we try to use some like kind of like a fancy method to make the transition of edge like smooth, and then when you look at this boundary, like looks better. Okay. All right. Okay. So with these fundamentals, then we're going to work on the images. Okay. So first the task we're going to talk about is segmentation. Okay. So here we use the CT as a CT image as an example because the scale is very, very clear. Okay. So what is this? Okay. So this is my image. Okay, so what is this? So in statistics, so basically this is a histogram of the intensities in my image domain. Okay, so if you look at this, histogram, so basically we see two peaks. One is around, basically the background because this is all, black, dark pixels, and this is bright, very bright. So we see another peak here. Okay, so basically it's simple. The naive way is that we try to play with some magic number, magic threshold. Okay, maybe the intensity is over 240. This is it belongs to the the skull, and if it's if the intensity is less than, let's say, 15, this is a pixel, right? We just set the threshold, and we can we can separate the brain. So okay, so here I use the threshold for separate intensity is 11, and the intensity threshold for separate to take the skull out is 185. So if you apply this operation, we can segment the the skull, segment the whole image to to the background, and this is brain. This is something we like, we're interested, and the skull. Okay, so this is a very naive. We call the threshold-based method, but it's not perfect because you still see something here, like some skull, because this is like too simple. Okay, so we need a more advanced method. So currently, for to segment the brain tissues. Okay, so basically this is the brain. So the problem is we want to give a label to each point in the brain image. Okay, we want to give, let's say, we want to give this the blue to the white matter region, green to the gray matter, and red to the the CSF. Okay, so how do we do that? So we study the intensity distributions. Okay, so basically we see there's the three clusters. Okay, so this is probably like something to do with maybe related to the background, and this is gray matter, and this is the white matter. Okay, but the problem, the challenge is there's some region we call the partial volume. Okay, so the partial volume is we call the partial volume. So what is partial volume? Partial volume is basically in here. Okay, let's do this. Okay. So let's say this is Gaussian distribution. Okay, this is another Gaussian distribution. Okay, their tail come like come across each other here. So for the pixels, in this location, it's hard to tell is this pixel, this pixel in this gray matter cluster, or this pixel is in the white matter cluster. Okay, so there's a lot of methods that we are using. So this is basically the threshold-based method. We just under the magic number, we try to segment the tissues into brain, into gray matter, white matter, and CSF. So if you look at the result, it's not so good because the reason I say that is because see, they have a lot of like noisy, like isolated green points here and there. So this is not it's not reasonable. Our brain does not look like this. Our brain, tissue should be something like very continuous. So we're going to see a uniform, a part of region, they are like a continuous, and it's kind of like a very homogeneous. So this is kind of like the result that we are looking for. Okay, so threshold method has limitation. It's very efficient, but it has limitation, and we can use k-means, right? We can use k-means. So basically, what I think you guys all know what is k-mean. How what the mathematics are, behind the k-means. So k-means is basically the kind of like EM algorithm. So we have the E step and we have the M step, right? So the E step, in the E step, we basically estimate, let's say here we want to cluster three, we want to assume there's three clusters, and we want to estimate, the mean and the variance for each cluster. Let's say I is for the cluster. So here I is 1 and 2 and 3. Then we have three clusters that we want to find out. So in the E step, we just try to estimate the mean and the variance. We have to assume this distribution for the Gaussian distribution, right? Otherwise, it will not work. Okay, and based on this, we're gonna to assign each pixel to a particular a particular cluster, and then in M step we can update the mean and the variance. Okay, so but the downside of the k-means is it only works in the it's kind of like a for each pixel like independent. Okay, maybe these 2 points, let's say they are connected. Okay, they are just like a neighbor, right? And it's highly possible if we just using k-means, basically 3 cluster. We only check how close of this voxel to the mean, and then we just assign a label. It's highly possible we give white matter, white matter to this point, and we give, let's say, gray matter to this point. Okay, and let's say in 2D, and we have another point. This is also white matter, and this is the this point is gray matter. Okay, because they're just so close. Okay, so close. So we're going to see, if we just use k-means, we still see some sparkles. Okay, some isolated points here and there. Okay, right. So the method, the current we are using, the classical method is we add a Markov, random field. So this is kind of like a spatial prior. Okay. Okay. We just add this phi on top of your your energy function. So basically we try to encourage the smoothness, right? So if, let's say, if there in this 2x2 neighborhood, the 3 are white matter, okay, and only these are gray matter. We're going to try to replace this gray matter to white matter, okay, and see by doing so if I can reduce my reduce the energy function. So the reason we add this random field is kind of like, you see, we just kind of like to encourage the spatial smoothness. So we're going to see, okay, it kind of like we're doing the smoothing. Let's say this structure. If we just use k-mean, we see that some it's kind of like not a continuous. It does not look like a real object, right? After we apply this constraint, it kind of like this shape. It's kind of like looks like an organ, right? Every part in our body is kind of like smooth, has smooth boundary. So this result is more reasonable to the k-mean. So in our current pipeline, so basically we are using this approach. Okay, so this is the very old technique. I think this is 20 years ago, but we are still using this. Okay, so it's called Gaussian mixture model plus the random Markov, random Markov field as a spatial, constraint. Okay, of course, right now you can use deep learning, but in most of the pipeline, we're still using this, this approach to do the image segmentation, right? And what's time? Okay, okay, keep up. Okay, yeah. So, but then sometimes we have if you work on the real image, there's another challenge. Okay, we call the bias field like this. The reason for the bias field is like if you have a camera, okay, and you take the camera has a flashlight. Okay, when you spot that the light has the lighting condition is inhomogeneous. Okay, you add this image to this image, you're going to see the image is kind of like a half. Some are very bright, some are very dark. Okay, so in the MR field, we call this is a bias field. So when we do the segmentation, you have to simultaneously estimate this lighting condition. Okay, so to regress this lighting condition out, then we can get the reasonable tissue segmentation result. Right. And the last part I want to talk about, this is not last, this is second last. Okay, so it's about image registration. Okay, so what image registration do is we want to, this is we call the source image, another is the target image, right? So they look different. So we want to find their spatial correspondence like for this one, we want to find the correspondence right here. They are corresponding to each other. Okay, so what basically the input is a two image, and we want to estimate a deformation field. So basically, for each point here, we're going to estimate a deformation dx, dy, and dz, and this is x, y, z, x plus x dx, y plus dy, and z plus dz. We're going to find the correspondence. Okay, so by doing this, we can, make the two image looks similar by applying the deformation field. Okay, so this is kind of like the black box of the image registration. So the input is two image. So one is called moving image. Another is called a fixed image. Okay, so basically we want these two images, they have different shape, different appearance. So we want to make walk the moving image to the fixed image space. Okay, so makes the moving after walking. We're hoping the moving image, aligned with a fixed image. Okay, so like this is the 5 fingers. I have another 5 fingers. Right, we want to walk. Okay, found the deformations to alignments looks like one hand. Okay, so basically this is a component in the image registration black box. Output is this is the transformation. We oftentimes we call it deformation field. It's kind of like this kind of deformation for each point here, and then we just walk. This allows to walk this moving image, make it look similar to the fixed image. Okay, so there's a lot of complicated math in there. So basically, we need a similarity metric to measure how close or how similar these two images, right? And so output is this transformation field. This is driven by the gradient. So everything is the most important part is here is the called optimizer. So we can use the so we can move to the next slide so I can help me to explain this idea. Okay. So the registration is basically it's going to minimize this object function. Okay. So basically we are looking for a deformation U. Okay. That deformation U allows if we apply this U to the fixed image, and then will look similar to my moving image. So this is kind of a similarity to measure, given the current estimation of deformation field, how close is the two images, okay? And of course, there's a lot of solutions to this U. It's a U-post problem. So we have to use some regularizers. The regularizer we often use is a Gaussian smooth. Okay, we want the deformation field like as smooth as possible. Okay, so kind of like a smooth like this, kind of it's kind of like a wave, like it's kind of smooth. Okay, so yeah, right. So the last part is I want to talk about is atlas. Okay, so we do the kind of segmentation is to get, so basically we want to know the structure in the brain. Okay, so this brain, this is brain. So we want to get this population. Each region is is related to the brain structure or brain function. Okay, so basically I give you this brain. I want you to do the coloring. Okay, give the color to each region. Okay, but this is a very time consuming. Okay, if we do the human, if we hire a medical doctor, it might take years to get this population, okay, because image is 3D. Okay, so atlas, so basically the teamwork. So we pick a subject, okay, and we have a group of medical doctors based on their domain knowledge. They're going to basically use the brush or the mouse to give the color to manually segment each region. Okay, it takes maybe it's a year effort, it's a team effort, but we only have one. Okay, we cannot do this for everyone. Okay, so if I give you, if you do the MR scan and we want to do the diagnosis based on your MR scan, right? So we need to first to segment the brain, and then we're going to study the shape, the volume of each region, right? So to do this, we need to populate these labels on the new brain. Okay, so what's the technology we need? Image registration. Okay, So we have this atlas, okay? So we basically we walk this atlas image to the new image, okay? Basically, we found the correspondence for all that, for every pixel, every point on the atlas to the new image, okay? By doing this, we can map this color to the new images. Okay, so this is called automatic, we have automatic pipeline to, to remove the skull, to walk the atlas to the new brain, and then we eventually we get this regions. Okay, right. So, okay, so this is the whole pipeline. So today I'm just today I just covered the first part. Okay, so basically this is for the MR. Okay, so the next lecture, Martin will be here. So he will talk about diffusion weighted image. Okay, so eventually the image is kind of, we can see the the orientation. Okay, that is basically the tensor image. Okay, after this, so using today's pipeline, we can get the postulation for each new brain. From the next lecture, we're going to get the we can study the fibers, and then we really know how these two regions are connected. Okay, and after that, we're going to get this structure connecting. So basically, we know these fibers in the brain, how this region connected to another region. Okay, using T1, the MRI and the DWI. Okay, and after we get this structure connected, we will have another lecture to talk about how to get the function connected. Okay, and then we get the graph. Okay, then we're going to do the the analysis. So, go to the next slide. Okay, so we have okay, so we have roughly 5 minutes left. Okay, so Judge is here, so she's the eye for this educational program. Okay, so she's going to show you example of MR image. Okay, so we're going to show you how to display the image. So ITK snap is one of the tools that we widely use in the field. So basically, this is a tool we can just plug in your image. You're going to see the image in 3 views, and you're going to see you can slide up and down, left or right. You're going to see protect the brain. And so we have the one example MR image, and she will be here, and we're going to show you how to install the software in your computer. It's a free software, and how to display the MR image in computer. Okay, and today I don't have time to cover the surface, so we're going to give you another surface file. Okay, so basically surface file is like this. So basically, when you open the brain, you look at this. So this kind of surface. Okay, we cannot see into this brain. Okay, but we can see the surface. Okay, so the parallel view is another software that we can display the brain surface. Okay, we will give you the 2 surface files. You can load it into the software, and you can just play around, and then this is kind of like how the brain looks like in the computer. Okay, so let me see. So two.
Can I get the permission to share?
She needs to share her screen. I'll share your screen. Yeah. Yes. All right. So today we only have 1 hour to cover some basic, concept of image processing. Okay? But when we work on the real pipeline, you will see. You are hoping that you understand what is segmentation, what is the registration, what is interpolation, or intensity, header file, image resolution. So those kind of concepts. Okay. So next, we're going to show you. I will let Judge to show you how to install that software and play around the MR image, so you can get some do some practice on the MR images.
Hi everyone, I'm Judge. I'm a research assistant at Course Lab, and I am a PhD student of the computer science. And I'll show you the. Oh, and this is my email. So if you guys have any question about the tools, just feel free to email me. Okay, the first one is the ITP snap. And you can just Google the ITP snap in the browser, and you can see this page. And here you can, based on your platform, to select the version that you want to download, and you can just install the ITP snap according to the instruction that's shown on your computer. It's very easy, and I believe you guys can do that well. And if you, like mine is the Windows, and if you click this, here's the form you can fill in, and it's very easy. And if you click the submit, you can get this page, and this is the download link, and you can download the ITP snap here and install it. And then next, I'm going to show you the example for the ITP snap here. And we have the 2-1 weighted images. So we can just I'll give you guys the those examples. And the first is original Nifty file, like load as the main image. You can just drag images into that snap. And this is the original one. And we didn't do like a small stripping, so we can still see the small here. And you can like screw the mouse to see the different slices. And this is the 3D views, so you can see the brain via the different directions, like here. And we can observe the direction in the other 2 views if you screw the mouse in this view, so you can observe in which direction it's moving. Like this. And also we have the brain images like this, also load as the main image. And we can see this is the brain. We don't have the other things like the skull, and this is only the brain. And they're basically the same, but this is only the brain. And also we can see the white matter and the green matter here. You can see those white part and the green part of the green matter, and the middle part of the white matter. And the last one is the, I need to mention that we need to load this label Nifty file as the additional segmentation, so that we can see the atlas, and the different color means the different region, and this is the labeled brain, so we can see the different regions here. Also, we can scroll the mouse to see the different slices. It's very easy, and you guys can play with those images with the ITP snap. And we have another tool called the ParaView here, and we can just also Google the ParaView in the browser, and you can see this page. And also you can download the ParaView according to your platform here. You can choose the Windows or the Mac. And I just download the first one and install this. It's very easy. I will open my ParaView to show you guys the surface. Okay, this is the, and this is the, and we need to open the eyes here. So that we can see the surface of the brain, and there are 4 lobes on the surface with the different colors here, and we can just drag the figure to see this brain in the different direction, and we can directly collect the direction, use the button here, so that you can see this in a different direction. And this is the whole surface for the whole brain. And if you guys want to say the surface with the edges, you can select it here. So that, oh, you can use the mouse to zoom in. And you can see there are a lot of triangular edges on the surface. So this is an example of the whole brain, surface of the whole brain. And if you guys want to just see the half of the brain, close this eye. Okay, that's all.
Thank you. Josh, you're gonna share those data with
On the
students?
website?
Yeah,
Mhm.
okay,
Sure.
sounds great.
You guys have that question about this? I think